Welcome to this explainer. Okay, today we are jumping straight into a really profound and, honestly, incredibly fascinating paradox of human biology. Have you ever wondered what exactly is going on inside your head when you're just staring blankly out of a window, or maybe lying in bed staring at the ceiling? You might think your brain is basically powered down, right? Just resting. But as we're about to see, the scientific reality is far more complex and, frankly, way more exciting than that.
So, let me ask you directly. What does your brain actually do when you do absolutely nothing? When there's no puzzle to solve, no conversation to track, and literally no task to complete? Well, for a long time, the assumption was that the brain just went into a state of quiet dormancy, kind of like putting your computer to sleep. But it turns out, the scientific answer to this completely shocked neuroscientists.
Okay, let's dive right into this, because the discovery of what your brain does at rest was honestly a totally happy accident. Back in the 1970s, a Swedish brain physiologist named David Ingvar was using this early imaging technique to map the brain, measuring blood flow with a xenon inhalation method. He looked at scans of people who were just resting passively, fully expecting to see super low activity. But instead, look at this vigorously active, brightly colored pattern here. The brain wasn't idle at all. It was working incredibly hard even when the person was left completely alone and undisturbed.
Now, as imaging tech got better in the 1990s with PET scans and fMRI, researchers kept running headfirst into this truly bizarre phenomenon that they called task-induced deactivation. Basically, whenever they asked subjects to do a hard cognitive task like, say, solving a tricky math equation or reading a dense sentence, certain specific regions of the brain consistently turned off. It's wild. These regions dropped their activity during external tasks, but the second the person was allowed to just sit there and rest, boom, they fired right back up.
To really understand why this is so weird, we have to think about how the brain normally interacts with the world. We usually expect the brain to light up in our primary sensory cortices. Those are the vividly colored areas you see here on this map when we're processing the outside world. Visual cortex for seeing, auditory for hearing, somatosensory for touch. These are the networks that anchor us to external reality.
And this brilliantly illustrates the contrast. Over on the left, we've got those sensory regions engaging with the outside world. But look at the right. Highlighted in blue, we have the regions that fire up when we do nothing. Notice anything interesting? That blue network, which we now call the default mode network, or DMN, sits just about as anatomically far away from those primary sensory cortices as it possibly can. It completely bypasses processing any external sensory input. This is a system entirely dedicated to the internal world.
Let's map out exactly what this network is made of. The anatomy of the default mode network features a few major hubs. We've got the medial prefrontal cortex right up front, the posterior cingulate cortex towards the back, the inferior parietal lobe, and the medial temporal lobe, which, you might know, houses the hippocampus, basically the center of our memory. And these aren't just isolated islands doing their own thing. They interact beautifully, like a perfectly coordinated symphony.
But what is this symphony actually playing? In 1995, researcher Nancy Andreasen and her team literally just asked participants what was going through their minds while their default mode networks were lighting up inside the scanner. Their answer? A mixture of freely wandering past recollection, future plans, and other personal thoughts. It turns out the DMN is the magnificent engine behind our spontaneous daydreaming, our mental time travel, and our deepest self-reflection.
And the craziest part? We can actually measure this mathematically. Researchers plotted how much people reported daydreaming against the fMRI signal strength in their default mode network. Just look at this clear upward trend line. It is a direct positive correlation. Literally, the more your mind naturally wanders and daydreams, the stronger the activation is in this exact brain network.
Essentially, you can think of the default mode network as the brain's ultimate internal life simulator. It pulls from the medial temporal lobe, which is basically your personal archive of memories, and uses those past experiences as building blocks to project you into the future. It's exactly what allows you to plan out conversations in your head before a party, navigate tricky social scenarios, and even imagine how other people might be feeling.
Now this brings us to a massively important question. If the default mode network is the core engine of our internal reality, what happens when this simulator breaks down? Because understanding this network isn't just a fun fact about daydreams, it's absolutely crucial. It's unlocking the biological roots of some of the most devastating neurological and psychiatric diseases in human history. So let's shift gears and really dig into the incredible clinical relevance of the DMN.
So, the crucial takeaway here is that there has to be a delicate balance.
A healthy default mode network gives us all that productive mind-wandering, memory retrieval, and future planning. But a disrupted network, that is strongly associated with things like hallucinations, severe memory loss, and a total inability to read social cues. The DMN holds the key to understanding major mental disorders. Let's look at a few specific examples to really see how this plays out.
First up, let's look at Alzheimer's disease. As you probably know, Alzheimer's is a progressive dementia that heavily impairs memory. Well, fascinatingly, clinical imaging shows that Alzheimer's specifically targets the posterior components of the default mode network. Patients show severe hypometabolism, which essentially means a drastic, damaging drop in energy use, right in the exact regions of the DMN responsible for pulling up our past experiences.
Now, what's really interesting about this slide is how visibly you can see this disruption across these brain maps. On the left, in a healthy young adult, you see those strong blue regions during an active task. That's the DMN correctly turning off or deactivating so the person can focus. In normal aging in the middle, it's slightly reduced, sure, but it's still doing its job. But on the right, in the Alzheimer's patient, that normal deactivation completely disappears. The network is fundamentally compromised. It just fails to toggle off.
Transitioning over to schizophrenia, we actually see the exact opposite problem. If Alzheimer's involves a hypoactive or underactive DMN, schizophrenia presents with a DMN that is abnormally hyperactive and overcoupled. It's like the brain's internal simulator gets completely stuck in overdrive and it absolutely refuses to quiet down when it's supposed to.
And here's why that is so disruptive. When the DMN is constantly hyperactive, the strict boundary between our internal mental simulation and the actual external world begins to blur. Because the network is firing so aggressively, patients might actually experience their own internally generated thoughts as external voices. And that leads directly to things like hallucinations, paranoid delusions, and severe thought confusions. The life simulator has basically overwhelmed their reality.
The default mode network is also really crucial for understanding autism spectrum disorder, or ASD. Remember how a key function of the DMN is theory of mind? Our ability to internally simulate what another person might be thinking or feeling? Well, clinical studies consistently show that individuals with ASD exhibit reduced activity and weaker connections within the DMN compared to typical populations. And that closely aligns with the challenges they often face in social inference and processing complex social cues.
So what is actually breaking inside the brain in these illnesses? Well, recent breakthroughs in neurobiology suggest the answer might be hiding deep within the brain, in an area called the thalamus. Researchers studying animal models have found that certain neurons act like a literal switch that controls the default mode network. And it looks like genetic variants that disrupt this delicate microscopic switch might be the foundational biological root of these massive network dysregulations we see in mental illness. It is a true game changer.
All right, let's quickly summarize the amazing journey we just took. The default mode network was discovered totally by accident by researchers who were just trying to get a baseline for a resting brain. But what they found instead was our internal life simulator, the biological home of our daydreaming, our memories, and our future planning. It operates entirely separately from our external sensory processing. And most importantly, understanding it has massive clinical relevance. It explains the mechanics behind the hypoactivity in Alzheimer's and autism and that devastating hyperactivity in schizophrenia.
So, the bottom line is, the brain is never truly idle. It is a tireless machine, constantly projecting us back into our past and forward into our future. But knowing all this leaves us with a lingering, almost philosophical question to ponder today. If your default mode network is constantly running in the background, continuously simulating and shaping your reality, who is really in control of your thoughts? Thanks for joining me on this explainer, and keep questioning the incredible machinery inside your own head.